Great. Good evening, folks. Nice to see so many people here, including some folk from Eigg. I can certainly see some names on the list. Nice to see you. I think we've got some experts in the room as well. Delighted to tell you the story of the third part of a series that we've delivered during this year's Scottish Geology Festival about just looking at episodes of volcanic activity in Scotland, and particularly how new understanding helps to really kind of show what's going on. If you want a more general introduction, just a reminder that last year I did a single talk covering the whole of Scotland in one go, which was quite ambitious. Look, there's a picture of Eigg, just because it featured. I also teach short courses at the University of Edinburgh, and we've got one that starts in January, which is delivered online, which is over 6 weeks. So that if you wanted to delve a bit deeper into other parts of the volcano story, then that also would be a great opportunity. My business is GeoWalks. I quite often do trips to Eigg and Rum. So if you want to see this wonderful geology in person, do come and join me sometime. The Scottish Geology Festival only exists because of the hardworking volunteers, including several of them here tonight. It's a great thing. It's coming to an end for this year, but it'll be back next year. We do need a bit of financial support to make the festival work. So please, if you haven't already, do consider joining the trust and or donating. Even small amounts do really help towards covering our costs. If you would like to find out more about the areas we're talking about today, I'll refer to a couple of important recent papers, but there's also these excursion guides published by the Edinburgh Geological Society, available online. So there's one for Rum, and John Hudson wrote with Anne Alright wrote a geology of Eigg a few years ago. I helped them to update it and republish it, but my name's on it, but it was really their work. I'll be using some of the diagrams from that book today, but particularly if you're wanting to go and explore for yourself, that's a great little book to have on hand. And finally, there's a really nice paper map published by the British Geological Survey, and it's a great kind of summary of the area. It's one of these very colourful and complex Scottish geology maps. It is accompanied by the green regional guide, Paleogene Volcanic Districts of Scotland, so loads of good information in there. That paper map is available to buy from the BGS shop. It is also available as a scan online, and that's in the link at the bottom here to the Maps portal. A really brilliant resource, which it's great. The Geological Survey makes not just the current editions of paper maps available, but all the paper maps they've ever produced, going back to 1832, and now also including 1 to 10,000 maps. So amazing stuff available at our fingertips to explore the wonderful stories of the geology of Scotland. Eigg and Rum are two very special islands. One of the things I want to show today is how different they are. And that's John Hudson there on the left with a group of people exploring the geology of Eigg. And one of the things he said in the introduction to the Geology of Eigg book, which really struck a chord with me, was this the special nature of these islands. Eigg in particular has got a very buzzing local community. A lot of things have happened there over the last few decades. Community on Rum is smaller, but also a lot of really good things happening. And I think the geology is very much underpinning all that, underpinning the whole character of this area. And what I want to show tonight is particularly focusing on the volcanic story, is just what an amazing story it is, how messy and complex it is, and how it's resulted in these range of islands through the Inner Hebrides, each with their special character. Focusing very much on Eigg and Rum tonight, but that the story extends to Canna and Muck as well, which are their neighbours. So just to set the scene, we're looking at the small isles within the Inner Hebrides, south of Skye. This is the simplified geological map of Scotland, available on the Scottish Geology Trust website, and you can see the key there. But I just really wanted to pick out the amazing range of ages for rocks here. If you're in the Outer Hebrides or on the Northwest Highlands coast, you've got a basement of Lewisian gneiss, parts of which go back beyond 3,000 million years ago. A lot of the area, including the original rocks of Rum, are the Torridonian sandstone, which are only about 1,000 million years old, so relatively young compared to what they're sitting on. But what's amazing about this area is the layers of geology. So we've got this very old basement, continental basement, affinities to North America, originally connected as a continental crust to Greenland and North America. The rest of Scotland has developed adjacent to this area, added onto this continent, new material created and deformed during the Caledonian orogeny. But we've got huge timescales. And when you're out in that area, in the area of the Minch in the Inner Hebrides, you've got this fantastic story of an ancient continental crust that got stretched and thinned, eventually forming the North Atlantic away to the west. But in this area, giving us the opportunity to add in some much younger rocks, so the youngest rocks in Scotland, and a mix of sedimentary rocks. There's a set of layers, Triassic, Jurassic and Cretaceous time period, sedimentary rocks with interesting fossils, plesiosaurs and dinosaurs and footprints. But sorry, we're not here for that tonight. That's another story. What we're interested in is the volcanic activity that followed after a bit of a break, but followed as the continental crust rifted and magma got produced and came to the surface and added volcanic rock into this area. So this is a regional map from the geology of Eigg, just to emphasize the connection between the islands. We've got lots of basalt lava flows in pink here across the area, Mull and Ardamurch and Eigg and Skye. Underneath that, you rate rocks in the Jurassic and Cretaceous, a little bit from the Triassic as well. Imagine really this is a build-up of different layers of types of rock over a really long time period, but also that this is one part of Scotland that has seen really intense erosion, partly due to the volcanic activity and uplift associated with it. So we've actually lost a lot of rock just in the last 50 million years from this area, where other parts of Scotland have been pretty stable and have much, much older rocks in many cases from this. So a burst of new activity, which both creates rocks, but also gives the opportunity for rapid erosion. So we take away a lot of that overlying stuff and expose the basement. So getting a really interesting mix. It's not just lava flows and volcanoes. We get to see the stuff below as well. And that's nicely illustrated from this view on Rum looking north. A lot of Rum, certainly in the northern part, is Torridonian sandstone, so 1,000 million years old. But that's the Black Coulee of Skye looking very impressive in the background there. So it's that variety of every view that you get in the Inner Hebrides, and the contrasts in the shape of the land, shape of the islands, and also the amount of vegetation, the way that people have been able to use this landscape in the past varies tremendously from island to island, just depending on that basic underlying geology and the variety of it. And there's a view from Rum, same sort of place, but looking in the other direction towards the mainland coast and this lovely low notched island of Eigg. They're very different. Egg's much more low-lying. It's also got a lot more fertility, and both islands have a long history of people living on them, but the type of landscape and the opportunities that have been available to people in the past have been very much controlled by that landscape and that geology. And the reason for the difference between them, the fundamental reason for the difference between them, is that there's a big fault line lying between them. So this is An Eigg, on the green fields at the back of Lag Bay, looking across to Rum, across the Sound of Rum, and it's only a few miles, but to contrast in scenery, the Camasunary Fault, named from Camasunary on Skye, and it runs south from Camasunary through the Sound of Rum here, and that's one of many faults in this area, but it's had a very strong effect in that the rocks on Eigg, the rocks on this side of the fault line, have moved downwards. So on Eigg, we don't see any of the old basement. It's there, but it's buried. So there's no Torridonian sandstone or any other highland rocks found on Eigg. Whereas on Rum, at sea level, we've got these rocks exposed. And in terms of the volcanic activity that followed, Eigg is lava flows, so stuff that erupted at the surface. There are some lava flows on Rum, but it's just a very small area. And most of the rock that you see in the volcanic complex of Rum has formed underground. So there's a difference just in terms of structural level caused by movement along that fault line. And that's the fundamental control of why these islands are so different. So here's the map from the geology of Eigg, showing the different rock units that you find on the island. Sorry, those of you watching the video probably have not been able to see the top right-hand side where the time scale is, but it's the same time scale from a few slides ago. So the yellow one here is from the Jurassic sedimentary rocks. There's a tiny little bit of Cretaceous, but mostly Jurassic. And because the whole island is slightly tilted, dipping to the south west, that means that when you go to the very northern tip, there's the older rocks are quite visible at sea level and above, whereas when you go to the south, all that stuff is just a little bit lower down and under sea level, so you just see the overlying lava flow. The interesting notched shape of Eigg comes from a fault line, which isn't drawn on this map, but runs across the centre of the island. And it doesn't have much effect in terms of what rock levels are visible, but it has just been a line of erosion and means that we've got that reasonably low valley going from the Glebe Barn through to the Lag, the gorge running down towards Lag, the north there. We'll talk about different elements of this as we go along. You'll see instantly from this map that we've got a lot of basalt lava flows, but we'll come back to the Sgùrr and the grey at the top, so the bottom of the map here, which is this famous pitch stone and lies on top of the lava flows. There's a few places as well, we're shown in this map in bright red, where there's been magma squeezed into the crust at a later stage, and that makes some interesting additional features. The writing in this might be a bit small for you to read, but it's not too important. I just again wanted to show you that the level of detail you'll find in the guidebook and how it all relates. So the main rocks on Eigg in terms of sedimentary rocks are Jurassic, so almost 200 meters of sandstones and mudstones, a bit of limestone, and then say 6 meters of Cretaceous. Allegedly, I've struggled to see it, and then a time gap. But then several hundred meters of basalt lava flows lying on top of that. Then the pitch stone, which comes later, and then at top, in some places, the glacial peat deposits, the blown sand, which covers over everything. But in terms of bedrock, two main units, sedimentary rocks visible at that bottom picture there, and the basalt lava flows on top. And as I said earlier, the sedimentary rocks are very interesting, lovely. These are some of the sandstones, beautiful concretions within them. There's been certainly a few hints of dinosaur found in this over the last few years, so really exciting stuff, and evidence of varying sedimentary environments back in the Jurassic period. But that's not what we're here for. We're looking at the volcanic activity today. And it links in with the development of the North Atlantic. So there's a lot of similarities with what we see in Iceland today. And this map for me really kind of brings home what makes this additional episode of geological activity on Scotland is so special, because along most of the mid-Atlantic ridge you don't get this volume of volcanic activity that you see in Iceland. You can trace that back to the beginnings of the rift splitting the continent and the beginnings of the Atlantic Ocean floor forming, and see this same vast amount of volcanic activity, which is really just on Scotland and runs down into the Antrim coast of Northern Ireland, but it's very geographically limited. But it's just happens to be that yet another special thing has happened here. Yet one more episode of geological activity that's given us this amazing range of geology that Scotland is so famous for. And the map on the right hand side just shows the extent of the areas of lava, and certainly there's been a lot of erosion. The lava would have originally covered the whole area from the north of Skye down through Mull and extending down into Antrim, kind of fitting within the existing landscape, and very much controlled in that it probably wasn't very much lava extending out onto the Outer Hebrides or onto mainland Scotland. It's very much within this restricted geographical zone. We just don't know its original extent, actually. But what's left is this amazing thickness in some places of layer upon layer of basalt lava. The best example probably to appreciate it is at Benmore and Mull, which is a Munro, and it's composed almost entirely by basalt lava flows of this time period. So that's a thickness of 1,000 meters, or there's probably much more in other places. Burying the existing continental crust, and while we talk about this being associated with the opening of the North Atlantic and what goes on today in Iceland, it is worth just reminding ourselves that this is within existing continental crust, so it is not new ocean floor, and that's what really helps to contribute to the amazing variety that we've got. So if you go to the north end of Eigg, you can see basalt lava flows about 61 million years ago, and they make these really rough cliffs. They're really are disintegrating in modern weather conditions, and particularly the conditions that have applied since the end of the last glacial period. These cliffs have been under attack by the climate and by frost, and so we get these tremendous piles of scree, and that applies in Eigg, Skye and Mull. Just so happens this picture catches a little bit of the sandstone visible on the left-hand side there. So you see this Jurassic sandstone. There's a big gap. There's quite a lot of time passed from the last visible formation of sedimentary rocks until the lava flow started and buried everything. And this picture just also catches another important part of the story, is that as well as seeing all this surface eruption, we get loads and loads of minor intrusions of magma seeping its way up towards the surface. So there's a line of basalt coming actually through the sandstone there, and loads of good examples. We'll come back to that in a minute. And so in terms of what it would look like on the surface, a picture from Iceland of fairly recent lava flow, and these typical very mobile red hot lavas that have spread out from fissures mostly. It would have spread a few miles from their source, and have then pressure of lava would have slowed down and they would have cooled, formed a nice solid layer, and then sometime later there'd have been another nearby eruption and the lava would have flowed out and formed the next layer on top. So that's just the sort of thing that's kind of routine in Iceland and would have been the picture going back 60 million years ago to this area. covering the entire area, not in a single lava flow, but in a patchwork of small lava flows from lots and lots of different sources. But geologically, very rapidly, we're talking about only just a few million years to form this thick accumulation of more than a kilometre of basalt lava flows. It's quite a story. It's quite an amazing thing to have happened here. And you see, lots of features of these lava flows on Eigg. They're eroding away, forming seaside cliffs. And in this left-hand picture, you can see ridges of different layers of rock running out to sea. So they're often slightly tilted. On the right-hand side, one of the cliffs in the north, and again, you get an idea of the individual lava flows, a few meters thick. There's a red layer halfway up the right-hand picture, which is a fossil soil horizon. So that's the top of one lava flow. And it means there's been a gap in time. There's been certainly centuries, thousands of years, that lava flow sitting exposed to the climate, starting to break down and having trees growing on top of it. It's a really difficult environment to preserve fossils, but the evidence from other places, Mull in particular, has got some great examples of the kind of trees that were growing in this environment. And in many places, actually, on the cliffs, you see that little strip of red. There's another one further up towards the top. So you get an idea of the thickness of lava flows. And just as we see today in modern equivalent environments, there's a gap in time before the next flood of lava buries the landscape. And these red soil horizons are very much part of the morphology of these lava flows, the different parts to them, which again, a picture from the Geology of Eigg guide to give you an idea. We've got a strong central part of the lava flow. It tends to be that as the lava forms and cools down, the gas content of it starts to rise towards the top. So you often get a more rubbly upper surface with lots and lots of gas bubbles in it. And that's the bit that's exposed to the elements and starts to wither, so start to form soil on the top there. And that's what's happened here in the left-hand picture. You can still see bits of grey basalt in here, but most of it's turned red. So this is iron compounds within what would have been a laterite soil at the time. No vegetation preserved, but we can assume that these lava flows would have been covered in trees. But the next lava flow comes out. The bottom part of the lava flow as well is a place which often has quite big gas bubbles captured in it. So the bottom part of the lava tends to be quite weak as well. And that's what gives rise to common shape of the landscape that we see on Eigg, but also really nicely displayed on Mull and Skye, called trap topography. I believe the origin's a German word for staircase, and it is that kind of staircase nature of the lava flows. These central portions, which often have cooled and contracted to form vertical columns, nice and tough. And then there's a weak layer on top of that, comprising the top of the lava flow, and maybe the soil and the bottom of the next one. And it's that weak layer that gets undercut. You can see it actually in this left-hand picture. The sheep like to shelter underneath that little crag, so they rub in and help to erode away the soft layer. But that means over time the cliff above gets destabilized. It's full of cracks, so you get bits falling off and rolling down the slope. And gradually the next layer up works its way back, and you get left with a stepped profile. I'll take a wee detour back in history, because one of the amazing things about particularly about Eigg, is just how it attracted a lot of geological interest in the past. And that was started by Hugh Miller, who visited in the 1850s. And he's well known across Scotland in terms of his fossil discoveries. And he wrote very evocatively, not just about the scenery and geology of Eigg, and he made amazing discoveries in just the few days that he spent there in a couple of summers. But he also described the people of Eigg Eigg, and he talked about the hardships they were undergoing. He was there principally to support his friend, who was the minister of the Free Church and had been forced off the land, and was travelling around the islands in the leaky yacht called the Betsy. So that book is The Cruise of the Betsy, and well worth reading. So Hugh Miller was the first to identify an amazing geology story of Eigg, and this was followed by many other people. And I just included this little bit from Alfred Harker, who very well known as a geologist, I think as a mineralogist principally, but he got a little bit full of himself, to be frank. And this is captured in this writing, how he's saying, oh yes, other people have been here before, but I've had the benefit of their knowledge and the new large-scale ordnance survey maps, and I've come back and fortified by these advantages, I've been able to pass with less diffidence from observation to inference and produce new results. And the funny thing about that was he got it completely wrong. So here's his map on the right-hand side, this black and white map, because he recognized the difference between these tough little cliffs of columnar basalt, which we now recognize as being the center of the lava flows, and the slightly weaker layers on top. However, he decided that the lava flows had just created the slightly weaker layers, and then after the big pile of lava had accumulated, there was more magma came up and just intruded into the center of all the existing lava flows. And for us today, it's a complete bizarre picture to imagine that kind of regularity of magma coming up. There's plenty of examples in Scotland of magma intrusion. Still, intrusion is very, very common, but to get 30 of them stacked up on top of each other, all of them separate, all of them squeezing into the middle of the existing lava flows, or the junctions between them, was a bit of a bizarre idea and didn't last for long. But that's this is his map, and you might not be able to read the details. The map shows the alternations of basalt lava and dolerite sills, which form Eigg. So that's yeah, so not everyone gets it right. And while it's, I'm laughing a little bit about this particular because he was so pompous in introducing the idea. But of course, it also helps to remind us of just how much knowledge has accumulated over the last 100 years, how much more we know about all these, all the ways that these work. And a lot of it's been come from accumulated knowledge of the geologists that have poured over this stuff, but also the observation of volcanic activity in other parts of the world. Let's move on, because very much a second part of the story of the volcanic activity is the intrusion of magma, not into lots and lots of sills as Alfred Harker had it, but most commonly as dikes. And it's one of the beautiful geological features, particularly visible on the west coast of Eigg. So this is near to the Singing Sands. The base rock at this level is the lower Jurassic sandstones, and there's loads and loads of examples of where magma has followed cracks and gone vertically up through the existing rock and then cooled down to form these really solid walls of rock. Geologists have called them dikes for 200 years, and they're given that name in Scotland because they often occur as walls of harder rock running across beaches with the softer rock eroded away. On Eigg, things are more interesting, actually, because this is an exposed coast. It gets battered by storms, and actually the basalt ends up not being particularly hard in that environment. It's still hard rock, but the cracks within it means that it is quite easy for the cracks to open up and bits to fall off. So the pebbly beach at the back there is full of pieces of basalt, a lot of them coming from the breakdown of these dikes. But you see how that dike actually runs up a gully up in the hill, and through the rest of the beautiful exposures of sandstone between the Singing Sands and Lag Bay, you get lots of amazing examples of small scale intrusions, never really huge. They're never more than about meter and a half wide, often much narrower. Sometimes they're ruler straight and you can follow them right across the beach. Other times they're nice and wiggly. Picture on the right here shows an example just beside the Cathedral Cave on the south coast, the southeast coast, and you can see a little stream of basalt coming up and pinching out there, a larger dike between it. They're connected to each other, and the magma is just finding weaknesses seeping through the rock, and you get lovely features in terms of chilled margin at the edge where it's still cool down quite quickly, and patterns of vesicles running up through them. And the map shows that distribution of the dikes, a kind of a schematic. They're really common right across the west coast of Scotland, and they often radiate out from the central volcanoes that developed in time. We're going to come on to in a minute. And so you get cracks radiating out, and the furthest of them extends from Mull right across into the northeast of England. So it's a big feature of this episode of volcanic activity, and runs all the way through the volcanic activity. Some of these will have been feeders up into lava flows. Others are coming up after the lava flows and cut right up through them. And as I mentioned earlier on, there are lots of other intrusions as well. There's some very fine-grained microgranites in the north. This forms the very northern tip of Eigg, and it's a sill, so it's been magma coming in horizontally, cooling down, forming columns, cracks that run through it vertically, and it forms these lovely big columns of light-coloured igneous rock. So just another addition to the big story. I mentioned the British Geological Survey's regional handbook. This chart is from that book, and it shows the three components of the volcanic activity in the Hebrides. So in pinkish colour, lava flows, first of all, and in many places, these surface lava flows covering the whole area are followed by a concentration of central volcanoes into a few places. So on Eigg, for example, there's no central volcano. There's a central volcano in Skye and in Rum and Ardnamurchan, and these are shown in the time charts as green. So in Skye, we've had 1.5 million years of surface lava flows, and then followed by many millions of years of central volcano activity, where there's been magma coming up into large magma chambers, feeding up to surface eruptions, but lots of intrusions and cone sheets and lots of other wonderful things going on. The dikes, the intrusions, are shown by the black lines cutting through it. So just to show you, these accompany the lava flows always, but actually continue along afterwards as well. So you get dikes cutting through the later big volcanoes as well. So on Eigg, we've got the first lava flows around about 61 million years ago, dike intrusion continuing for a little while afterwards. But we're going to move on now to Rum, which also has early lava flows, but then has the development of a central volcano 60.5 million years ago. This map comes from a very good introductory source. If you want to read more about it, there's a really nice series of booklets produced by what was called, then called S&H, British Geological Survey, about 15 to 20 years ago. They're all available as PDF files on our website, the Scottish Geology Trust. There's about 20 of them. Some of them have been republished more recently as a series Set in Stone by Alan McCurdy. So if you want to buy them, they are available, but free. And this is just a nice summary map. The Torridonian sandstone takes up a large part of Rum, so that's the existing old continental crust. But the main focus of the volcanic activity on Rum is this area of blue and purple, centred down to the southwest of, just southwest of the central point of Rum, and most of that is magma chamber rocks. and amazing story. It's been really well studied over the last few decades. Lots of geologists have spent an awful lot of time crawling around different parts of Rum and developed a really good understanding of a very messy, complex magma chamber, which is formed within existing volcanic material. So there's around the edges of that, there's some surface volcanic eruptive material, so it starts off being pretty explosive, and there's also a big wodge of granite out to the west. So it makes for a very interesting landscape. All this is pretty hard rock, so it forms the Rum coolant, but it's got a lot of detail within it. So just to give you some ideas of some of the range of landscapes and features that we get from all this geology. This is north side of Halaval, one of the high peaks in the Rum coolant. And it's got beautiful layering that you see from a distance, horizontal layering. You'd be forgiven if catching sight of it from afar to think it was sedimentary rock, but it's not, it's igneous rock. And this layering is the result of accumulation of different crystals from the massive magma chamber. Plus also some later intrusions. People, I think, are still arguing over the detail of how these things form. But there's certainly, while overall it's basaltic in composition, there's a lot of variation in terms of which kind of crystals were forming at different times. And so you tend to get lighter coloured rocks, troctolite, which have got a lot of feldspar in them, and just a little bit harder forming layers. And then the other layers like peridotite and gabbro have got a lot of olivine in them, break down a little bit more readily. And so you see on this slope, there's actually quite a few places where you can't see the bedrock and it's turned to soil. Incidentally, this is the place where the shearwater nest, and they're taking advantage really of that geology because they're finding some soft layers that they're able to create their burrows in, but high up in the mountains, protected from predators. So really taking advantage of that variation in igneous rock. If this was just one pile of gabbro or granite, even worse, there wouldn't be that variation, wouldn't be that weakness for them to exploit. So the interior of Rum is a pretty harsh environment. You get a lot of rock exposed, not much soil, not much vegetation, but these beautiful shapes coming from the breakup of very dense, coarse-grained igneous rocks that are formed within a magma chamber. But there's a lot of olivine here, and olivine does tend to break down quite readily in this sort of climate. So you get a lot of brown, crusty rocks and beautiful textures and shapes. If you get a chance to see the layering close up, and it's not always visible, it doesn't apply everywhere, but there's some spectacular examples in the centre of the island where you can see the detail of layering at different scales. And this is showing the accumulation of varying crystals as the chemistry of the magma changes with time, but a complex magma chamber that keeps getting refreshed by new magma coming into it, so the composition of it varies, and you get these alternating sequences of different rocks. And an opportunity to get into a magma chamber that, of course, we can't do with a modern volcano, but actually lots of visible features showing the complexity of magma moving around, of rocks, crystal cumulates forming and getting disturbed. So there's a block here which is withered away and left a puddle behind. There's another one over to the right hand side, but both of these have been solid lumps which have rolled down a slope or plummeted down onto the floor of the magma chamber, and you can actually see how they've smashed into the existing crystal layering and deformed it. So the sort of thing you would see in a sedimentary environment, but here we're talking about within a magma chamber, and pieces of rock that have already formed from the magma getting dislodged and tumbling down. So loads of amazing detail, which really nicely described in that geological excursion guide to rum that I mentioned earlier. You could certainly spend 2 or 3 weeks very happily crossing rum and seeing the full range of amazing things that have been discovered there. And just here's another little fragment. The Lewisian gneiss lies deep beneath the Torridonian sandstone in the west coast of Scotland. But on rum, it's at a much higher level. It's within the volcano, surrounded by some of the edge of that volcanic complex. There's some explosive material. And so the thinking is that this is a very deep piece of the existing continental rock that's actually been brought up hundreds of meters from its source, just sitting there quietly. It's only a couple of 100 meters long. It's easy to overlook. I'm sure I would have overlooked it if I'd been doing mapping here, but yeah, pretty amazing story. It's it's the journey that's been on. That ancient rock formed, this rock, Lewisian gneiss, finished forming 1800 million years ago, and so that rock spent 1800 million years, almost 1800 million years under the surface, quietly sitting there, and then the volcanoes erupted through it and brought it further up to the surface to expose it in the center of Rome today. And in the west coast, the northwest, a completely different landscape where the granite is eroding into the sea. So it's an interesting range you see along the top surface there, just that very kind of typical granite scree developing on the surface as this rock breaks down. So as we see on Skye, where the volcanic activity includes this big gabbro magma chamber, but there's been associated with that the formation of melt, a completely different chemistry, and they've stayed separate and risen. This granite magma has risen up together to give a really nice contrast. Time to move on. But just to finish the story in Rum, we go back to our chart from the British Geological Survey. The green marks a few 100,000 years in which that central volcano was active, but it's then followed by more lava flows, and they're actually seen on Canna as well. And they just add this lovely extra bit to Rum. This is the beach at Girdle in the northwest, and a lot of the pebbles there are the base rock of the north of Rum, the Torridonian sandstone, but there's lovely smooth grey pebbles of basalt as well. So there's some lava flows, particularly in the north, forming a couple of the ridges. And one of the geological curiosities in one of these lava flows is the bloodstone. So there's a little green fragment buried in the pebbles there. If you look across the beach, you see lots of this. And this is a form of chalcedony, which forms within the lava flows. It forms within holes and vugs within the lava by later hot water. It was called bloodstone because it got little specks of red in it. But as chalcedony, as a flint-like rock, it was really important in the past because that's not a kind of rock you find a lot on the west coast of Scotland. So it was found on Rum, quarried on Rum, and traded across the western seaboard. It was used for making sharp blades. And then later it was a kind of jewelry curiosity, a gem curiosity. So it was actually quite a deep mine dug high up on the hill on Bloodstone Hill. So yeah, just another tiny little fragment, very much associated with the lava flows that come in. So there's Bloodstone Hill, Girdle Bothy down at the bottom there, and this lovely green slope with basalt lava flows at the top, and that's where these green fragments are coming from. And these lava flows extend over onto Canna, but they're mixed in with layers of conglomerate. So they're mixed in with these lovely big rounded boulders that have been washed down from the high ground in Rum. So again, looking from Canna, we get some basalt lava flows here, slightly younger than the central volcano on Rum, which is in the distance there. And so we've got this nice picture that the main volcano on Rum's extinct. the top part of it's eroded very, very quickly, and it's formed high ground with torrents of material being washed off in all directions, but also lava flows, particularly associated with further volcanic activity further north that are flowing around this area and accumulating mixed in with the layers of debris. So none of these places has a simple story of just one thing happening and then another. As in the case of Rum, we can see the progression of the volcanic activity and the return of basalt lava flows. Which brings us back to Eigg, because the youngest bit of the geology of Eigg is An Sgùrr, the beautiful pitchstone ridge that runs across the south of the island, and it forms this really impressive topographical feature, which has been a magnet for geologists in the decades after Hugh Miller first described it. It was argued over quite a bit. And then people kind of felt that the story was known and lost interest. But as we'll see, fortunately, somebody came back. Anyway, the Sgùrr is just the end of this ridge, and it runs westwards, a bit north, right over to the western coast of Eigg, where it comes out onto the cliff there. And it's a really impressive high ridge. It looks great when you arrive on Eigg from the ferry. It looks like one of these impenetrable pinnacles. But if all you can manage is a day trip to Eigg, and that would be sad, to be honest. Do go for longer if you can. But it is doable. It's one of these beautiful Scottish mountains. It's actually a lot easier to get up than it looks. In fact, it's maybe the only Scottish mountain that's easier to get up than it looks. So it is a really pleasurable walk to get up onto it, and there's a path that takes you along the north side to a nice easy climb up onto the ridge. It is pretty high, it's steep cliffs, but you can, most people don't have too much trouble getting along actually onto the high point. But it's not just that bit. That ridge continues. There's Rum in the background, and this high ridge of grey rock just meandering across the island. It is superb, and you can see that the top of it is columnar. In fact, the whole thing is columnar. So you're walking on the top surface. It really does feel like you're walking on something even more impressive than the Giant's Causeway or the island of Staffa without the crowds. It is really quite an amazing feature to explore. And this is what it looks like close up. So it's called pitchstone, which is a pretty unusual type of rock in Britain, and it really is volcanic glass. So it's actually a black glassy rock when you get it fresh. The grey colour that we see in these previous pictures is all to do with the weathered surface. But when it's broken, it's glassy and full of plagioclase feldspar crystals. So you see lots of little crystals within it. And so pitchstone glass implies quick cooling. Here's a side view of the ridge. The high point is on the right hand side, and if you come up onto the ridge, you walk along this section above this cliff, which is on the southern side of the pitchstone. So you can get an idea of columns. It's got some big cracks running through it, and it's also got these pale grey stripes running along it in places, and that's an important part of the story. So as I mentioned, it's been explored in the decades after Hugh Miller first described it. There was a bit of an argument about how this pitchstone formed, but eventually it was agreed that it filled in a valley. So the existing basalt lava flows were there first, and there was a gap in which a steep-sided valley was eroded by a river, and then the pitchstone filled in the valley. And Archibald Geikie was very taken by it. He used it as an example in his Scenery of Scotland, very well known at the time, and as just capturing the evidence here of erosion and how they've got different stages of erosion here, because the original lava flows have been eroded. There's a big river valley cutting down through them, and then that river valley's been filled, and it happens to be filled with the harder rock. That means that it's ended up being a reverse topography. Is that the valley fills that ended up being the hard material that has survived. Underneath the pitchstone, the evidence for it having formed in a valley was that there was big boulders underneath. Hugh Miller found some tree fossils buried underneath it. So again, that vision of geological time passing by and there being this deep valley with big boulders and trees growing in it, and then a new volcanic layer forming on top. So it's also from Archibald Geikie, this description of the curious layer down at the bottom. So here's the grey pitchstone at the top here, but the very lowest layer is this jumble of fragments. It's all a bit altered, but it seemed to be an important part of the story, that there was a peculiar decomposed section at the base. Talking about the passage of enormous lapses of time, and they're just a good example to show to people the rich story of Scotland's geology and all the wonderful variety that it has. Here's a close-up of the area beneath the nose, end of the Sgùrr Ridge, the brown withered basalt lava flows. You can see how they're cut by erosion. And then the pitchstone has accumulated on top of it. And the pitchstone itself, this black glassy rock full of feldspar crystals, also has columns. And the base of it, the columns are quite broad and rising up at an angle. But you might be able to see it in this picture. I'm not sure it's too clear, but the entire top section has got these lovely smaller columns as well. So a very complex body of rock. And here's the view from the other end. Again, you sort of pick out a valley shape there. The existing lava flows have been eroded. I've never been to explore because it's ridiculously steep, but I'll take people's word for it that there's boulders in there, boulder beds. So the river valley, and then this pile of pitchstone on top. And pitchstone's an interesting thing because it's so silica rich. It's rhyodacite composition, so it's right up there. And one of the problems with that, when you look around the world today at volcanoes of this composition, it's really rare to get anything like dacite and rhyolite that can flow as a lava flow. But that was the assumption, that it just so happens to be in a lava flow that kind of went down a valley. And there was some discussion about that weird gunky layer down at the bottom. Had that been the result of some ash flow, and then the lava flow had kind of slid along this. But it was really unsatisfactory. It just didn't make sense in terms of what we've learned over the last 50 years about how volcanoes operate. And there was also these curious light-coloured layers of other rock that were within the pitchstone that I showed you a picture of a minute ago, because they were thought to be intrusions later coming in, which is, again, it's really hard to explain. How would magma intrude in close to the surface along a lava flow in a river valley? It's almost getting back to Harker and his amazing story of the lava flows having lots of little intrusions. So, but anyway, it sat there for a while, a long time. One of the additional bits of geology locally, which is intriguing, is the island of Sgùrr out past Rum, which is also pitchstone. So widely separated, a very uncommon rock across Britain, but we get two lumps of it close by, but actually separated by quite a distance. What was the source of this lava flow, and how come it had been preserved in these places? There's another view of Sgùrr with the good yacht Selkie in the background. I don't know if Celia's in the call tonight. I know some other Eigg folk are, so I should promote our geo sales while I'm here. Celia and I run regular trips in the west coast of Scotland. We've got one planned for next year, visiting amazing places by yacht. It's a beautiful yacht and a great team of people involved in exploring the islands. Okay. So it's all better now. That puzzle, that unaddressed nature of the volcanic rock that forms An Sgùrr was solved by this publication 10 years ago by David Brian Bell, which instead of forcing us to struggle with the complexities of a lava flow creeping across the landscape and filling in the river valleys, actually gave us this beautiful vision of this being an ignimbrite. So it looks like a lava flow, but it's actually an ignimbrite, and that's really ties in with increasing recognition of how volcanoes erupt, the kind of rocks that are formed from explosive volcanic eruptions, and this idea that there could have been a nearby eruption which buried the whole landscape, filled in these river valleys with a very quick, thick accumulation of hot ash from repeated pyroclastic flows. And then the whole thing had kind of consolidated and formed a really hard pitchstone layer. So this is our revised diagram from the new edition of the geology of Eigg that shows, instead of it being a lava flow, a blast, and the whole area is covered in volcanic ash, but it accumulates thickest in the river valleys and ends up with present-day erosion, leaving it as an upstanding ridge. And I think Davey's here, so I'm very hopeful that he'll answer our questions later. But this is a picture from their paper. This very rapid, I think we're talking about just a period of perhaps a few days. Lots and lots of pyroclastic flows bringing ash into this area, very hot and very quick accumulation. Their paper is pretty technical, but the important things really is that we're talking about the ability of that hot material as it gets deposited to turn into that solid glassy rock. And they also had this idea that actually some of it would kind of remelt, and that there would be localized areas where there'd be little kind of puddles of melted material that would then crystallize to go a slightly different rock. So that matches with these pale layers I mentioned earlier in the sides of the hill, which had previously been interpreted as later magma intrusion, which is a really difficult thing to explain. The whole thing's accumulated quite fast and then cooled down, and columns have formed within it as it's contracted. So beautiful explanation, and really helps to solve a lot of problems with that occurrence, that volcanic activity, long after everything else on Eigg has finished and cooled down and been eroded, to get this blast activity. And of course, the big question is, well, where's the smoking gun? Where's the volcano? And back to the chart. BGS made an error in the chart, and 58.3 million, actually saying the text is 58.7 is a date for the formation of the Sgùrr of Eigg. And the problem with that is that there's no volcano locally. Rum has very much erupted and gone. And we know that from the lava flows that lie beside Rum that formed afterwards, and the erosion, already a lot of erosion. Rum would have been probably not looked that much different from how it looks today. There might have been a bit more volcanic rock there, but it's already eroded away within the few million years after it erupted. And the only possible local volcano is on Skye. So in terms of time, that's the only possible source, and that certainly fits with the rocks on Skye, the red cool in the Skye, and some volcanic rocks there. So that was the original suggestion from Brown Bell's paper, and then it was picked up by other folk a couple of years later. A little bit more work and tying together the little bit of pitchstone we see at An Sgùrr, also on the Sgùrr of Eigg, and possibly a ridge to the south of Muck. So suggesting that actually in this zone south of Skye, there's actually quite a lot of volcanic rock of this type and this age, which could have come from the same source. Not necessarily just a single eruption, but possibly a whole series of really big silica-rich, ash-forming eruptions, which we just happen to have tiny little fragments of left. So it turns it into a much bigger story, actually, and a really amazing story to imagine. Really must be one of the last significant volcanic eruptions in the British Isles. They're really coming at the end of a lot of volcanic activity in this area. But the idea that some of that silica-rich magma associated with the big granite formations that we see in both Rum and Eigg, Rum and Skye, but some of that actually causing some really impressive ash clouds, pyroclastic flows, and cooling in some places to form this pitch stone that happens to have been preserved. So, a great story, and what I love about the combination of different things here is how there's a lot which is just wow. It's just the sort of geological story that you see elsewhere in the world. Basaltic lava flows are really common around the world. It's common to get big accumulations of them here. We've got this really special situation in the west coast of Scotland where these lava flows are sitting on top of a really interesting variety of other rocks. So it's not just large areas that are buried under basalt. Much as we love lava flows, we do have to admit that basalt isn't the most exciting rock in the world. But the addition of the central volcanoes here, so that on Rum you get some of the subsurface stuff, you get the remains of an exhumed big basaltic magma chamber with all the interesting features that are in there, plus the granite and the lava flows nearby. So lots of interesting contrasts just in a small area. And then the icing on the cake, the last bit of the story, that we get preserved just little bits of what is probably a much bigger story, but giving us intriguing geology to study, but also really contributing to the attractiveness of the island of Eigg to have this lovely pitchstone ridge preserved. So if you don't live there, go visit, because these are just two of many islands on the west coast of Scotland, but they've got beautiful geological stories. They're interesting places to visit, and the contrast between them, separated just by a few miles of sea and a big geological fault, the contrast is great. I've been going there for a while. I hope I'll continue to go there for another few decades, but I'll finish off there, and it'd be great to chat and ask questions and hear from some other people as well. Thanks very much.